this week. Lab 1, the part of lab 1 that you have to do on your own is due before the start of the lab. And this week there are no classes on Wednesday. As you all know, it's due to TRC. So because of this, what we're going to do is actually so for lecture, there'll be no lecture. So don't come on Wednesday. For lab, if you have a lab on Wednesday, then you have one of two choices. One is you can do it on your own, right? Download the lab. The lab is online. Just do it on your own. And then come to GLC, come to office hours, and ask questions on Piazza. The second option is you can go to a different lab this week. Just for this week only, if you have lab on Wednesday, you can attend a lab on Monday, which is today, or on Friday. Sorry, today we don't have lab, so it's actually Tuesday, Thursday, or Friday. So those are your options. Okay, so you're still responsible for the lab, even if you don't have a lab on Wednesday. So you have to figure out how you want to do that. Assignment 2 is up. All of you have done assignment 1, or most of you have. Looks like the grades are pretty good across assignment 1, actually. So it looks like most of you figured it out. So assignment 2 is going to be due. Assignment 2 is going to be due on Monday of the following week. So it's going to be midnight on Sunday. So just like the assignment that was due last week. Okay, great. So let's move on to more fun stuff. So last time, really the last week, we covered a lot of stuff about models. So data models and control models. Right, so we covered things like flow graphs, and then call graphs, and then UML sequence diagrams, and UML class diagrams. So all of these we're trying to get you to think about code, trying to get you to think about code that you haven't necessarily wrote and didn't quite know how to understand. And the most complex of these were this sequence diagrams that we covered on Friday. So what I'll do now is I'll actually review the sequence diagrams So we'll just build it together again, and we'll build it for the check game over method within the SI game. Okay, so this is just going to be a review of the UML sequence diagrams, and then later on we'll move into abstraction and talk about data abstraction. So I'm just going to start it here. So the UML sequence diagrams, remember, it's attempting to model what happens in a method when you are at a particular instance in time. So someone called this method, which is check game over, right, on an instance of the class SI game. And now you happen to be executing this method. And you can simulate it by putting a breakpoint and actually simulating the method as it executes, right? So the UML sequence diagram is going to show us what happens when you execute this method. Okay, and this is what we're going to draw in detail. But first, there's this thing which says assumptions. So what are assumptions? Do any of you remember from last Friday?
If there's only 2 missounds or 1 missound,
There's only 1 or 2 what?
missound. So like say something.
Well, in this case, is that an assumption we need to make? If you look at like the there's an invaders list that is used in this loop, right, that I'm going to highlight. So, since we're looping over actual objects, we have to kind of say how many we have. And quite possibly we have to tell you more about those objects because we might operate on them. Right, so since this is detailing the actual execution, you have to provide all the details that we need to actually simulate this method in the UML sequence diagram. So the first thing we need is to say, how many invaders do we have? Now it doesn't have to be 2. Okay? So 2 is just a random number. It's a nice number for class demonstration purposes that we chose on Friday with the missals list. Here we have invaders and we can choose any number we want. Okay? So let's choose 3 this time. Okay? Just to make it a little bit different. So our assumptions is going to be invaders contains 3 invader instances. Remember, instance mentioned, is the same thing as an object. An instance is an instance of some class. So an invader instance is an instance of the invader class. So we have 3 of those. What other assumptions do we need to make? This method is a little bit different from the one on Friday.
We need to assign a value for next get y greater than height each time.
Yeah, so this is a little bit tricky. So here, inside this loop, I'm saying next I get y. Remember, next is pointing to some invader within the list of invaders. And I'm executing this method. So this method is going to return some value. Since I'm simulating this, I'm going to have to actually draw it out. I have to tell you explicitly ahead of time what that return value will be. Okay? And I have to do this for every invader because next is going to go through every invader. So I have 3 invaders, and so now I'll say, for first invader, y, let's say it's greater than height, which is this constant in the program. And now I'll say second and third invaders have f height y less than height. You all see why I need this assumption? All right, so I'm going to execute the code. And every time I evaluate it, I'm going to have this question of, okay, so get y is executed. What happens next? Right? Do I execute the statement or not? And I need that. I need to know what the invaders actually contains and what their properties are. So that's why I'm making this assumption very explicitly at the beginning, before I do anything else. Okay, so now the sequence diagram. How do I start this thing? What do I need? Yeah, so I have, to start with, this thing is being called on something, this method, check game over. It's being called on some instance of SI game. So for that instance of SI game, I need a lifeline. So here's one. Right, so I'm just going to call this guy a SI game. And the type of this guy, what kind of SI game is it? It's just SI game. Yeah.
Did you choose those y values arbitrarily or in a matter of reason?
Arbitrarily. Yeah, so for an exam, for example, if you had to draw a sequence diagram for this method, you'd have to specify exactly what the assumptions were, or we have to give you the assumptions. Okay? You can't draw the diagram without assumptions. So, I have this lifeline. So remember, time is going down, right? So the first thing is, this method is going to get called, which is check game over. Check game over. So now I'm at this point. What happens next? Does it just execute within this method and doesn't leave it? Yeah, so I need another lifeline, but then lifeline is going to be for which object? Which object do I need? So invaders is a list, right? But to start with, I'm going to just look at the method calls, right? So the method call here is going to be next I get y, and this method is called on some instance of invader, right? And this is, when I run the first time, it's going to be the first invader. So take your trusty little ruler. Draw another invader. Draw an invader. It's going to be next. Invader. I'll just say this is the first one. Alright, so now I'm in this method. I have to call get y. And then I return back. Now, this is the first invader. By assumption, my y is greater or equal to height, or greater than height. So I've executed this statement inside the if statement. So is game over is now true. You have to keep that in the back of your mind, okay? Because we're going to get to the point where we're going to use that knowledge. But right now, this statement is not going to appear in the UML sequence diagram. because the sequence diagram only captures method calls. Okay, no statements. So just think about the fact that is game over is true, so game is over. Right, the invader reached the bottom. Okay, so what happens next? So I have 3 invaders. I needed to tell you that there are 3 invaders because probably I'm going to use all of them, right? This is why we have assumptions.
So we'll get y for the next.
Go and get y on the next invader. Okay. So I have another next. It's also an invader. This time I'm going to do the second one. Okay. And now I call get y on the second invader. Return back from it. And the same thing is going to happen for the third. I have a next. It's an invader. The third invader. And now I'm going to call get y. Third invader. It gets messy with multiple objects. Okay, so now I've executed this loop 3 times, right? And each of the next instances is diagrammed here because they're actually pointing to different objects. Yeah?
So for the second instance of invader, isn't y not as, isn't y less in height? So how is the third invader?
Yeah, so what ends up happening is that this thing is evaluated to false. So we're not going to set this thing to true, right? But it's already true from this first box, right? So if you look at this box, I can use little boxes to denote execution. So within this first box, I executed that statement. Within these 2 boxes, I haven't executed that statement. But that statement doesn't appear in the actual diagram. Okay? Yeah.
Instead of having like an assumption where you first, second, or third invader, could you do something where you have like next invader first and then dot dot, and like next invader and then just draw it?
You could. There are actually ways of depicting that in UML sequence, in UML in general, but we're not going to deal with that now. Do you guys see my assumptions? Were they visible? So basically, here are the assumptions, right? I have these 3 invaders, and then I have the lifeline down below. Okay, so what happens after this loop? What happens next? So I'm running through the code, I ended the loop, I get to this statement, right? Does the statement evaluate to true or false?
True.
Why is it true? Well, because why is game over true? It's because we've executed a statement, right, on the first iteration. So we executed the statement exactly in here. So that means that the next thing we do is we're going to execute these 2 statements in this body of the if loop, of the if conditional. For that, what do we need? Another lifeline, actually 2, right? So each of these things is a list. You can just hover over it. List and list. So I need 2 lists. I need a list of invaders and a list of missiles. So now it's going to get tricky. So I have many more things to draw. So I have my invaders. I'll just say it's a list for now. And missiles. Continue this lifeline. All of them. And I'm going to call each one. I'm going to come back for each one. And I'm calling clear on both of them. Clear and clear. So then my method ends, and I come back. I return 2 whoever called me. Wow, really big. Yeah, that's it. That's the full sequence diagram for this method, right? With the assumptions that were above. So I have 3 invaders. The first of them is going to make this if condition true, and then the other 2 are going to make it false. Okay? So it's a little tricky because you have to keep some things in your head, and then you're going to have to state up front some assumptions so that you can use them within the evaluation of this method. Yeah?
Is it possible to exit the for loop once you've found one missile that's exceeded the height?
It is possible. That would be an optimization.
How would you do that?
How would I do that? There's a statement called break in Java, which will allow me to exit the loop. Okay, so that's UML sequence diagrams. This is just a review, but hopefully you'll be practicing these further. Okay, now back to kind of this review. So we were talking about models, and we're going to stop talking about models. So models are really useful for understanding code, right? So back to this diagram again, where you have this source code, and the source code, you can use it to extract different models to understand what's going on, right? But the source code itself is implementing some abstraction of your domain, right? So for example, if you had Space Invaders, like I said last time, you might represent that game in different ways, right? So you might, make it three-dimensional, or you might draw Space Invaders differently, right? So your implementation, right, is going to implement objects from this abstract domain. So another example is if you're going to implement an application that allows you to register for classes, right? So that application can be used in any university, and that application is going to have to take into account things like how many students there are, the fact that students have names and addresses, and the fact that students are associated with certain classes, and certain classes are located in certain buildings, and there's so many buildings. So all of this stuff, it's all in this domain of abstractions, right? That is going to be true regardless of the university, right? And regardless of the actual students, right? So there will be a student abstraction, a data abstraction that represents student. And then for each of you who are registered in this class, you would instantiate it. You would actually create a student instance, right? So this program is attempting to implement something from this domain of abstractions. And this is what we're going to talk about today. Really, the question is, how do you build abstractions in Java or in any programming language, really? Because abstractions are really just very fundamental programming language. So this is kind of the view of abstraction. Now, let me actually show you a couple of examples. So one example is in this missile, the missile class that you all know. So you have SI game missile. The missile has a constructor, and the constructor allows you to create a new missile. Now, it's an abstraction for a missile, and it's actually an abstraction for multiple missiles. Right? Really, the way to think about abstractions is that an abstraction is something that can represent multiple concrete objects. Right? So this missile is an abstraction for multiple missiles because it abstracts away the coordinates of the missile. Okay? So I can create a concrete instance of a missile at position 5,5, or at position 2020, or at position 3030. I'm still going to be reusing the same abstraction. Right? And this is really useful because now I don't need 5 different missiles, each one at specific coordinates. I just abstract away the coordinates. So another example is actually from Racket, where you have some code here. So here's like a really simple expression that just computes the area of the circle with, radius 10 and radius 14. So you guys should have seen this in your last class, right? So the idea here is that I'm just going to put those together and then compute the area. And I might compute the area for different circles with different radiuses, right? Different radii. Now, of course, if I keep doing this, it's going to get boring really quick. So what I want to do is abstract away from these statements. I want to apply procedural abstraction, where I'm going to create a procedure that takes an argument to generate each of these expressions. And that procedure is simply down below, right? All I'm going to do is define an argument, r, and r is a parameter to the function. And what I've done now is I define the function that can generate either of these. And that's really useful, right? Because I just wrapped that expression into this more abstract representation. So this is an example of procedure abstraction, where essentially we're pulling out, arguments that range over some domain, and we're going to pass them to a method as parameters. So we're going to instantiate a version of this expression with 14 and then with 10 to regenerate the things that we need. So this is very procedural. So the stuff we're going to look at today is actually going to be data abstractions, which are a way of representing data. Stuff that you might want to do with data in memory or data from the real world. And so the example that we're going to use is actually going to be, so here's a bunch of questions that we're going to consider. So here's some questions that you should be thinking about or you should be able to answer at the end of 3 lectures. Right? So really the questions have to do with data abstraction. So first of all, how do we specify? Like we keep talking about this data abstraction in very generic terms, but concretely that means writing some code. Okay? So what kind of code do you write for data abstraction? And then how do you use it? Right? So I keep saying that it's useful in some way, but what does that mean? And then how do you test that the abstraction that you created is actually correct? Right? So this is a very common problem because you often have bugs in your abstraction. Right? So you might, for example, assign a student to 2 different classes that are happening at the same time in the same day, which is a problem with your abstraction. Right? It's not concretely, in reality, it's not possible. But if you encode it into the program, it'll be possible. But that's a bug. Right? Because your abstraction is incorrect. It doesn't represent reality. So you'll be able to figure this out with testing. So that's going to be our technique for actually verifying that your abstraction fits the specification. And then finally, how do we actually implement it? So to start with, we're going to do this little exercise with sets. So math is really fun. Raise your hand if you think math is fun. All right, great. So math is really fun. Why is it fun? Because it's really abstract, right? So the math domain is just really perfect for programming because you can do things that are very convenient and flexible in the math domain. You don't have the same restrictions and so many conditions as we would in the real domain. So we'll basically just deal with this data abstraction of a set that contains integers. Integer set. Okay, so what are some key properties of a set? Like how would you define a set? A mathematical set.
In a very broad sense, it's just a collection of elements, and those elements can be whatever you want. I mean, in a sense, it can be integers, but...
Right, so if you have an integer set, give me an example.
Of a set in general?
Of an integer.
Okay, set, okay. An integer is 1, 2, 3, 4.
1, 2, 3, 4. This is fantastic. Look at this. We have a set of integers. Really simple. Right, so math is great because I can just write it down and you know what I'm talking about. Cool. Okay, so this is a set of integers. Is this a set of integers?
Yes.
Oh. Okay, good. Good thing we're doing this exercise. So this is not a set of integers because I have an element 2 which appears twice in the set, which is illegal. Right, so a set must contain only unique elements. So this is not a set of integers. Okay, what about 1, 2, hello? Is this a set of integers? It's not, right? So, set of integers contains integers, and each of those integers must be unique. Very simple to define, right? Now let's actually try to represent it in Java. So, just going to start writing some code for you guys. And we're going to start with specification. So, usually when you specify data abstraction, you talk about operations that you envision on the data abstraction. So this is a set of integers. So what kind of operations do you need for a set of integers? Add. Okay. Usually we call it insert. So you might want an operation called insert. So insert an integer. into integer set. Of course, we're going to have some kind of constructor, this being Java, right? So create an empty integer set. What are the operations that we're going to want? Remove an integer from the integer set. Okay, anything else? What can you do with this set abstraction? Like a set is really great representation for like a group of students. So what might you want to do with a group of students? Append?
Put two sets together in one.
Two sets together into one. So that's a really strange operation. So if I have set 1, 2, 3, and another set 2, 3, 4, what happens if I append them? 1, sorry, yeah. 4. What do we call this operations on sets? Union, right? Union. Combine two integer sets. What else? Intersection. Intersect this integer set with another one. And return the intersection. Okay. What else? Fine. It's interesting. Usually you say contains. Check if the integer set contains an integer. Any other one? Look at like take the sum of all the integers. Okay, let's call it like get sum. Find the sum of all of the integers and return it. So what I'm doing here is I'm actually specifying this data abstraction. Right? I'm specifying it in terms of the operations that I want it to support. I'm not implementing it yet. I'm telling you the kinds of things that are feasible with the data abstraction. Like the kinds of things you can do. Right? And so, as you would imagine, each of these are going to be turned into a method. Right? Because method is how we do things in Java. Right? So, let's kind of sketch that out. So, the constructor would be something like public integer set, and it'll just be empty. So this is how we create an empty integer set. Right? It just doesn't have any body, it doesn't return anything. Well, it returns an integer set. What about insert? What does this look like? Okay, so I might have public void, and then I have a method, and a method is insert. Is this what I want? Well, parameters, right? I mean, this insert tells me that it inserts an integer. Where's it going to get that integer from? Right? So the obvious place to get that from is to require the person to give you an integer. Require the user of this data abstraction to give me an integer. Okay, so I'll give integer I as an insert. Does this look right? Yes. Like many integers? Well, this inserts a single integer.
Yeah, so you take argument of one integer and one integer set.
Well, this thing is going to operate on an instance of the integer set. So when I call this thing, it's already calling on this instance. Right? So we're really defining properties of an integer set that's already been instantiated. So another way to declare insert is to have insert return a Boolean value. For example, I could have insert return true or false depending on whether inserted an integer or not. And that'd be a different specification for the same method, right? But you get to sort of choose. We get to choose because we're creating it. Okay, what about remove?
public void remove integer I?
Very similar to insert. When I remove an integer, I need to get an integer as input, so that's going to be my parameter. And then internally, I'm going to somehow modify the representation of an integer, right, to reflect the fact that I removed this element. Okay, let's do just some more. What about contains?
I have a question. What happens if you don't tell Java you're going to pass the parameter, say integer I?
If I remove this guy?
Yeah.
Well, you have a bug in your specification. So I just told you that this thing needs to remove an integer, and how can it possibly remove an integer, right? There's no way of knowing what exactly it's removing. But we'll get to that. We'll be kind of drafting this out, and we'll get it to a point where it's much more concrete, right? So right now I'm just kind of want to sort of sketch out the declaration of the methods, the operations that I want to execute on the integer set. So let's do contains. Let's do one more.
Public boolean contains integer.
Contains integer I. So this boolean thing comes into play here, and here we actually do need it. Because this thing checks if the integer contains an integer set contains an integer. What it really means is that it needs to return something that tells us, does the set contain it or not? In order to communicate that back to the user of this data abstraction, you have to have a return value. And in this case, it's going to be Boolean, it's just true or false. So for now, so now Eclipse is going to give me a compiling warning. It's going to say this method must return something, so I'll just have it return false. That's like, just to get it, to get rid of the debugging mistakes. Okay, perfect. So now, we're going to talk about so let's talk about the clauses. So here on the board, I actually wrote down the 3 clauses that we're going to cover today. One is requires, the other one is modifies, and the last one is effects. So those 3 things will be in every kind of specification in this class that you will care about. And those will actually kind of pin down the data abstraction. Right, so right now it's very arbitrary. It doesn't tell you, when it is legal to call insert, when it is illegal to call insert, or what happens when you call insert. So to specify these, we're going to use those clauses.
In the remove method, what if you also want to be able to remove an element in the set using like the position? Say like I want to remove an element in position 2, but you don't know what it is.
Well, that would be great, except that a mathematical set has no position.
Okay.
Right. So 1, 2, 3 is equivalent to a set 3, 2, 1. Right. So if we actually want to capture a mathematical notion of set, right, then position doesn't make sense to model. We could if we wanted to model a list, for example, or a set which had positions, right, like a list with unique elements with positions. But in a sense, here we're modeling a set, so since this is true for sets we want to represent, that means position is not one of the things we want to represent in the data abstraction. Okay, so let's do some requires clauses. So the way to think about requires, and typically the way we're going to specify each of these, we're going to have this top level comment on top of each of the methods. It's going to be in all capital letters. So requires basically has to state what is necessary in order for me to call this method. Okay? So in some sense, I'm going to evaluate this condition that I'm going to write in requires. And if it returns true, then it is legal to call this method. So integer set is, this thing is a constructor. It's always legal to call this method. Right? So what kind of expression do I need that evaluates to always true? It's just true. Right? So when I write true here, it means it is always legal to call this method. So there are no requirements that I need to satisfy in order to construct an integer set. you can always build one. Let's do insert. What does insert require?
Don't you use set to begin with, in a way of numbers?
Yeah, you need a set to begin with, but insert is already called in an instance of a set. Right, so in some sense, in order to use these methods, I'm going to have something like integer set s equals new integer set. So now s is an integer set. I just created it. And now I can call s.insert. Yeah, 5. Or maybe not. Sort of depends on the requires clause, right? So whether I can or cannot execute this method depends on what I'm actually going to write down here in this comment. So what is necessary?
I needs to be an integer.
So I needs to be an integer, but that's kind of obvious, right? That's already in the parameter list.
Oh, it can't already be in the
Aha, that's an interesting one. So one requires condition is that I cannot be already in this list or in this integer set. So notice that here this is kind of a special keyword. Right? Remember when we looked at SI game, this represents the instance of this class, of the integer set class. And I here references this argument, this parameter. So this parameter I cannot be already in this integer set. Right? So when I call s.insert 5, right? If I call s.insert 5 again, this is an error. This is an improper use of this data abstraction. And how do you know it's an error? Because you can look at the requires clause, and you can say that, oh, this s right now contains the element 5. So 5 is inside of 5, so that's an error. Questions?
What is the difference between requires nothing and requires true?
There's no difference, except that you write requires nothing as requires true. So when there's nothing, no requirements, then you want it to evaluate the true. Think of it as a kind of a logical expression, right? That you evaluate it at the time that you're going to call the method. And if it evaluates to true, then it's legal to call the method.
So it's the same. It's writing down requires nothing.
Isn't it remove checking that?
Checking what?
Checking that 5 is not inside the set already?
Well, what is the requirement for remove?
I is already in the set.
Okay. I must be in this integer set. So, one interesting thing to note here, maybe this is what you're getting at, is that these requires clauses specify what is legal or illegal based on something that we came up with in this class, right? So someone else could have come up with a different specification for the integer set. For example, it could be legal to call remove. For example, maybe they said, oh, you can call remove whenever you want. Let's just require true. And then internally we'll check if I is already in the set. And if it is, we're not going to do anything. But then the specification we just came up with is stricter, right? In the sense that there are fewer cases in which you can call remove. And we require that I must already be in an integer set. So this is a design decision, right? So there's no rule that tells you that this is the right way to specify the integer set data abstraction. Sort of depends on how you're going to use it. So that's really important, right? Because so there's a reasoning behind why we made this requirement, but that reasoning may change depending on the circumstances. And so this is our design at the moment. So we also have this contains. Let's fill out the requires for contains. So what does contains require? Yeah, so we could require that the set is not empty, right? In order to check if it contains anything, maybe we require that it has some elements. I think it's a better specification to just leave it as true. Just to say that, well, does it contain the integer I? Actually, you don't know, whether the set is empty, whether it contains 5 items or 6. So this thing is going to check for me. So I don't want to kind of over-specify it. I don't want to put too many constraints on when you can call this method. Okay, so now I have this requires clause. So this this catches out kind of the specifics of what we expect from this data abstraction. Now the next thing that we're going to need is the effects clause. So the effects clause is something that tells us, what happens after you executed the method. What is going to be true? Right? In some sense, the one way of thinking about this is that requires is something that we require from the user of this data abstraction. Right? So we require that the user, cannot call this thing if I is already in the integer set. And then the effect is going to be something, it's going to be a promise. It's going to be a promise by the data abstraction that something is true after you've executed the method. Right? So the requires is a promise by the caller, effects is a promise by the data abstraction. So what's the promise in the constructor? What do we know after we execute the constructor? What's going to be true? Set is created, right? So we say the effect is this returns a new empty integer set. So that's my effect. Basically, effects, you can think of it as them describing an implementation, but maybe a better way of thinking of it is that it's a version of the implementation that's visible to the person that's using the abstraction. Right, so how do I actually create this set, this integer set? I don't know, I do a bunch of statements, they create lists or they create arrays, maybe they allocate memory, whatever they need to do. But at kind of at the high level, as a user, all you care about is that this returns an integer set. And that set is going to be empty. Okay, what about the effects of insert? What is the promise made by the insert method?
It inserts an integer into the set if it isn't already included.
Right. Well, we know that it's not already included. Right? Because that's the requirement we put on the person using it. So the effect is going to be that I is an element of this integer set. So the effect is I is now part of the integer set. Okay, what about the effects for remove?
I is not an element of this integer set.
Absolutely right. I is not an element of this integer set. Okay, the last one, the last clause that we'll cover is modifies. So modifies is a funny one because it really talks about kind of state changes. So what is this method allowed to change in the program? And the reason we specify this is because it's really important. It helps us to reason about a method if we know the kinds of data that it changes. Right? And modifies, in essence, constrains what can happen. So right now, if it modifies is everything, then you really can't reason about other state in your program because everything could all of a sudden change. All the missiles could be moved. The tank could be anywhere, right? Invaders could go up and down. So we need to kind of constrain what can happen based on the state that will be modified. So integer set just modifies this. Right? It modifies this integer set. That is, this integer set. Just write that as this. Constructor is always going to have this property. It basically modifies this because it needs to build this object. When you're building it, you're modifying it. Insert modifies, also going to be this, right? Because we're going to change the state of our integer set. And remove. Also this, right? This is kind of boring. They're all this. So when you write modifies, you really have like three options. One is that you modify the fields of this method, and once we add fields to this class, we'll go back and update the modifies. Okay? So we'll actually tell you exactly which fields have changed. The other thing that could happen is that you could modify the integer, like the parameters that actually pass into the method. So it could be that modifies is actually I. Right? It modifies the parameter that's passed into the method. So if that happens, you have to document that in modifies. And then kind of the third category of things you might include here are things that are modified externally. It's like these implicit objects that simply exist in your system. Yeah?
For the fun things, why does it modify this? It doesn't modify the set, right?
Perfect. You found a bug in my specification. Modifies nothing. This is why I choose one, right? So the bug here was, well, contains just checks if it contains an integer. It shouldn't modify anything, right? So we'll just tighten the modifies clause, right? We'll constrain it further. We'll say you can't change anything within this method. You can compute, but you can change.
What are effects for contains?
Effects for contains? Oh yeah, did I miss that? What are effects for contains? Returns true if I is in this integer set. Otherwise, returns false.
How do you write the modifies for, say, union, where you have, it would be this and a second integer set?
Yeah, the second integer set is going to be maybe a parameter. And so if you're modifying that parameter, you'll include it in the set of, in this modifies clause. So we'll actually list it. Okay? Okay, so this is our specification for this very simple implementation. Now, just to finish off, let's look at the missile class within the SI game. So the missile class, remember it constructs a missile. And this class already has some of these specifications that we talked about. So for example, the constructor constructs a missile. And the effect is that the missile is positioned in coordinates x1. So this is another example of where we're using these same clauses to kind of tell us what the missile represents and what is supposed to happen. And then here on the bottom, move modifies this because it has to move the missile. And the effect is the missile is moved through y units. So a really good exercise to do is simply go here and then add the effect, add the modifies, and then add the requires. Right, for each of these methods. So right now some of them are missing. So this is a partial specification, if you will. We don't have complete information about what the missile is supposed to do. So in truth, you need this for everything. In practice, not always possible. Okay.